you for coming. I know you're all tired, and so I'll be brief. I don't have much to say, so I can at least show another pretty picture. So in my talk on Wednesday, I was arguing that the forces of the lattice of vortices in the inner crust, and I'll stay completely in the inner crust in this talk, is sufficient to pin vortices throughout much of the inner crust. And that pinning effect acts as a sort of gyroscope in a body once you excite a precession mode. It tends to make the precession extremely fast, of order the spin frequency, or say 1% of the spin frequency. We have very compelling evidence from a number of isolated neutron stars that precession is occurring over time scales of order several years. So the question is how to reconcile pinning, which predicts fast precession, with observations that imply very long period precession. So I'll give the bottom line of my talk so that you can stop paying attention after this point if you're tired, because I'm going to get into some technical detail. My claim is that if the pin vortices creep, that is, move slowly, with low dissipation, then there is a long period under damped mode which could account for precession. That will be the claim of my talk. So I want to get into just some of the detail that leads to that conclusion. So Costas described how vortex pinning can be treated as the high drag limit of vortex motion. And to repeat some of what he said, and mostly just to establish my notation, the idea is let's equate the Magnus force on a vortex that's moving at velocity VL with respect to a background superfluid moving at Vs. Equate that Magnus force to the drag force. So in this is superfluid density, the quantum over vorticity, and this is a unit vector pointing in the direction of vorticity. And then to write down a drag force in the frame of the solid that depends on the vortex velocity. So the most general kind of thing you can write down is this first, is a piece that depends on drag, that determines drag along the direction of vortex motion with a coefficient eta. This was R, script R in Costas's notation. And then in generality, you could put in a piece that is orthogonal, transverse to the motion of the vortex with a different coefficient, eta prime. And then the argument is that if you want the vortices to stop, you put in this drag term, and just for the moment, let me neglect, as is typically done, eta prime compared to eta. That's thought to be small compared to eta, even though neither is known, and generally set to 0 for reasons of simplicity. So let's do that. Let's assume that's negligible. Then, if I want the vortices to stop, that is for VL to go to 0, thus representing pinning, then I can do it by making eta enormous. As I make eta very large, then to make sure that this is not an infinite term to compare with a finite term, we have to make VL go to 0. And so what is often done is to model pinning that is achieving the VL to 0 limit by taking this drag coefficient to be infinite. However, that's not true in general, and that's what I want to emphasize for the rest of my talk, is that if you put in a non-dissipative force like the pinning force that I was talking about on Wednesday, I can in fact throw away this drag force and stop the vortices. So if I were to throw this away completely, and it would go away because it depends only on VL, then VL goes to 0, and that just says that F naught has only to be equal to the Magnus force that's exerted on the vortex. Okay, if that's the case, then the drag coefficients can be, in principle, anything at all, even small, and we still have pinning. So though it's a convenient way to model pinning by saying that the high drag limit corresponds to pinning, to say that that's true in general, I'd say smacks of skullduggery.
No, sorry, you don't have, that's not convincing. You didn't even sound, Chris used skullduggery in a very natural way.
Yeah.
This
is obviously forced.
10 minute forced build-up. I think
it was forced. I wanted to get it.
But well done.
So we should at least. So what I'd like to do in the rest of the talk is say, well, since we can have these pinning forces that can stop the vortices, we should let the drag coefficients be anything. and entertain the possibility that they might be small. It's a physically completely plausible limit. The dangers of saying that vortex pinning amounts to high drag is that when you start calculating modes associated with differential motion between the superfluid and the solid or some other component like the protons in studying a mode like precession, is that modes tend to damp when you put in a lot of dissipation. If you turn down that dissipation, then you get a different kind of mode. So here's the mutual friction force with references to prominent Russians that in slightly different notation than what
I think all the
Costas wrote
are
down.
surprised.
Some of them.
When I next see them, I'll tell them that you think they're Russian.
No, some of them are. Some of them.
Sorry.
I put in some. So the mutual friction force is often written in this way, and I'm doing everything in the rest frame of the crust, where we're just looking at superfluid velocities and line velocities with respect to nuclei that are stationary in our frame. So the way this is often written is that you have a force per unit volume contribution that is in a direction orthogonal to both the superfluid flow and the vorticity. That's one direction, and we assign it a coefficient beta prime. And then there's another piece that is in yet another orthogonal direction, which, if you work out these cross products, turns out to be parallel to the superfluid flow. And we give that a coefficient beta. And these are phenomenological coefficients. Then, if you impose vorticity conservation from the equations of motion that I showed you on Wednesday, then this force must be equal to the cross product between the vorticity and the relative velocity of the vortex line, VL, and the superfluid. So you can compare this side to this side, and you can solve for VL in terms of VS and these coefficients. So what you get is a component along VS that's controlled by the coefficient 1 minus beta prime, and then you get a component that's orthogonal to that, which is controlled by beta. So in the limit of vortex creep, the line velocity and magnitude is much, much less than the ambient superfluid flow. If the vortices were unpinned and there was no dissipation, they would simply move with the superfluid. In the creep limit, they're just barely moving, and the superfluid is moving by high velocity. So in the creep limit, both of these coefficients are small in magnitude, say much less than 1. If you calculate the dissipation rate per unit volume, it is determined by the projection of the vortex line velocity on the direction established by the cross product between the superfluid and the vorticity. So if I have vorticity this way, and so the superfluid is going this way, this is the orthogonal direction into the void. That's basically the direction of the Magnus force if the vortices were pinned. And so it is actually the velocity of the vortices along the orthogonal to the flow that determines the dissipation rate. And that's related to the coefficient beta that's appearing in this expression. That determines how dissipative the vortex motion is in terms of these phenomenological coefficients. So low dissipation corresponds to having beta be very, very small in some sense, such that this dissipation rate per unit volume becomes small. So what I'd like to consider is a particular limit of low drag. Let's assume that not only are beta small and 1 minus beta prime small, but beta further is much smaller than 1 minus beta prime. That is, this ratio is much less than 1. But this ratio, if you look at these two terms in the expression for VL, is simply the tangent of the angle that the vortex line takes in the presence of this mutual friction force with respect to the ambient flow here. So what the vectors are is, here's the solid through which the vortex line is creeping. The superfluid is flowing to the left in the board. The vorticity is up. And then when there's dissipation, the vortex moves on average at some angle into the board, theta d, the dissipation angle, so away from you guys. And this ratio that I'm talking about is the tangent of that angle. And the limit I want to consider, which I think is completely physically plausible, is that that is much less than 1, which means that because dissipation is low, the vortex moves almost in the direction of the superfluid, but with a small component into the void. Geometrically, that's what that limit means. So to do the mode analysis, I followed the method of Strakian, Wasserman, and Cordes, and what this does is basically to say, okay, we don't know the boundary conditions, and we don't know the boundary conditions between the solid and the internal liquid, and we don't want to deal with gradients in the force throughout the system. So what you do is you take the mutual friction force and you form the local torque density and just integrate it over the volume. And this is not studying the full hydrodynamic problem, as Kostas was discussing. However, I think it's useful for looking at the effects different choices of mutual friction coefficients can have when looking at modes. So when you do this, you get a set of equations that look like...
I'm confused. I think you're talking about exactly the same limit as you talked about.
Well, that's the weak
No,
mutual friction
no,
limit,
no.
right?
This is a weak damping limit, but the beta prime, I think beta
Ah,
prime
okay.
being more close to 1 is when you push the R parameter that he has to be very large. Then you get this beta prime goes to 1 and the beta is very small. I think you're talking about exactly the same.
So yeah, this is the
Good.
strong mutual friction limit.
However, your R is this eta, is it not?
Yeah.
I am not in that limit of eta being large.
Uh,
I am in the
But
limit.
you're-
No, you are.
Your beta and your beta
Yeah,
prime.
no,
are
No, no,
very-
I said no.
No,
No,
eta,
no.
wait. Eta makes no sense anymore in this description because I'm putting this
Yeah,
in.
but no, sorry. I was going to
Yeah.
ask this, so let me ask it now. Where does that F node show up in your hydro?
It doesn't, well, I'm not doing hydro. Except in this one.
No.
Except
On
it-
the next slide, you're slapping down Sedgwick and Wasserman and Cordes. They're
Yeah.
doing hydro.
Yeah.
So, I think that your F node, your statement is the F node, I think, it sits in beta and beta prime.
Yeah.
Right? Now, so it's hidden in beta and beta prime. Now the claim I would make is that if I take the other view, that there is no F node, but I'm going to construct an F node out of the eta,
Yeah.
then the eta sits in beta and beta prime,
Mhm.
and the limit that Kostas is talking about is exactly this limit that we call the creep limit, where the beta is very close to 1, and the beta prime is very close to
Okay.
1, and beta is very small.
All right.
So we need
Let's
to...
work that out.
We should
Yeah.
work this out.
That could be.
Because
That
if
could
that
be.
is then...
That could be.
Yeah,
Maybe
just-
here there's a confusion because what you call low drag for your single vortex dynamics is not that does not immediately translate to low drag over the fluid element dynamics.
Yes, it does. It's given by this expression. So I'm just insisting that beta be small enough.
Yeah, but
That beta be small.
yeah, but let's say that you kill your drag, your eta.
Mhm.
Still, your vortices can pin. They can stay pin. So
Yeah.
now, if I consider the behavior over a fluid element scale, on the fluid element scale, that would correspond to strong drag on that scale. So there is not one-to-one correspondence. This is what I try to. That was my message on my slide. That it's not clear how you average your result to hydro mutual friction forces. So even if you have zero drag in your calculation, when you average this and you build a hydro mutual friction force, then you can have strong drag on the hydro scale. So I think your result, the one you showed few days ago, that you have been vorticity anyway, no matter what's the mesoscopic vortex drag, I think that corresponds to strong drag at hydro, no matter what is your eta.
I think that makes no sense because it showed that there was pinning with zero dissipation in the system.
Yeah, but this is dissipation. This is the dissipation you
So,
use for
I
the
mean-
dynamics of a single vortex.
But so I'd be interested to see how you do averaging over fluid elements that have zero dissipation and you get strong drag.
But the strong drag limit is non-dissipative. You just have the vortices
That's
fixed.
right. The
Yeah.
beta...
No, infinite drag is non-dissipative.
Yeah,
Let's
I think
consider
you can.
finite drag.
I think we can sort this out later. I
Okay.
just wanted
Yeah,
to
okay.
understand, because I mean...
Maybe it's the same. Maybe it's the same. I have some
Well,
different notation, but can we agree that this is the creep limit?
Yes.
And that if I'm allowed to make beta small, I can make the dissipation per volume small.
Absolutely.
That's all I want to do. Maybe it's the limit you're considering. But I'm talking about a different problem anyway. I'm talking about precession. Okay?
So here's a possible way out. That limit, the last equation,
Yeah.
does not come out. It's not the same limit as the large eta limit.
Yeah.
Right? And so then there's the magic is in how, the pinning force comes into this prescription, the top equation.
Yeah.
And that I don't know.
Yeah.
And I think that's the one we need to think about. If you can come up with a prescription that gives you the top line, then
Okay.
I think
Yeah,
that
so
would be
so
better.
what I'm, well
That's
actually,
not so obvious.
with the spirit of what I'm doing is that if you do all this, and then you read off the line velocity, this is a perfectly legitimate decomposition into components of the line velocity. So, and then we can just tune these coefficients, so it looks like what we've been doing with mutual friction, but what I'm really talking about are effective coefficients in the mutual friction.
I'm happy with that.
Okay.
And I suspect that
Yeah.
bottom line, when we write it out, that's
Yeah.
not going to be the same.
You said not?
It's not going to
Yeah,
be
I think the bottom line would be violated
Yeah.
when you write beta prime in terms of my R.
It turns out if you go back and you play this game, where we don't put in F naught, the only way to make this inequality be satisfied is if you make eta prime enormous. You make this eta prime enormous. Yeah. So what you would need to have a low drag situation is eta small, but then the way you stop the vortices is have eta prime enormous. But when you put in the pinning force, then basically I regard them as arbitrary parameters. Okay, so this is the limit I want to explore. On to what Sedrakian, Wasserman, and Cordes do is you integrate these torques over the volume of the star, and when you do that, and you further assume that the superfluid doesn't have any internal differential rotation, but rotates with one angular velocity, essentially as a rigid body, then the equations of motion for the crust and the superfluid look like Euler's equations in classical mechanics, but with torque terms that are determined by these mutual friction forces integrated over the fluid. So the left-hand side, just to bore you with this a little bit, I crust is the moment of inertia tensor of the crust, and that contains any information about deformations and oblateness, for example. Stars indicate time derivatives in the co-rotating frame. Then we get the usual cross products of the crust rotation rate with other things that are determined by the transformation into that frame. But what I want to draw your attention to on the right-hand side is you get a mess of terms that depend on these effective mutual friction coefficients beta and beta prime. Then you can put in an external torque, which I've done in these calculations. And you get a corresponding equation for the superfluid. So if you take these equations, and we admit that we're not doing full hydrodynamics here, but still just look at this as an exercise for exploring what different choices of beta and beta prime do in this model, you can take these equations, linearize them, look for fixed points, and calculate modes in this framework. So if you do that, you get a mode, an interesting mode with low dissipation. You get one mode that is the very high frequency mode. But because now the vortices are moving slowly, there's a very slow mode, and it takes the following form. If you write the mode amplitude as proportional to I, some frequency t, some complex frequency, and solve for that complex frequency, I omega has an imaginary or oscillatory part and an damped part. So the oscillatory part is determined by the ratio of the moment of inertia of the principal about the principal axis of inertia of the solid to the superfluid moment of inertia, epsilon, however much oblateness the rigid part of the star has, times that one of the mutual friction coefficients, 1 minus beta prime. And then the damping rate is determined by the other one, by beta, the dissipative part of the mutual friction. And so I assume that both of these are small. Epsilon is small for typical deformations we've been considering. 1 minus beta prime is small. And so this mode has a very low frequency, is a very low frequency. If you tune epsilon and this coefficient to small enough values, then you can get a precession period of a year. then, but this mode should be under damped to be physically reasonable, so beta must be much less than 1 minus beta prime, which was what I assumed in the first place, but we've got these other factors to contend with. So in the end, a low frequency under damped mode is possible when this ratio is much less than some oblateness times this ratio of moments of inertia. And when you put in the numbers, I think it is not unreasonable, especially since we don't know what these coefficients are. So to conclude, I would say that pinning is not necessarily incompatible with long period precession. You can get a slow, under-damped mode, and this just highlights the fact that we need to calculate mutual friction coefficients, something I've been talking about with Sanjay. Thank you.
So Bennett, how do we picture this mode? I know what's really going on in the precession. If I want to picture it in terms of motion, this is fluid and the
Let's take an oblate star with angular momentum like this, and then I pin the vortices along this axis. This is the configuration of minimum angular momentum for, or sorry, minimum rotational energy for fixed angular momentum. Now, we perturb the whole thing, so then some sort of slow wobble of the crust, or actually the crust begins to wobble, and then it executes a slow retrograde roll about its symmetry axis. Now what the vortices are doing, I have more difficulty visualizing that. They're moving slowly, but they're doing something similar. They're processing, they're wobbling in a way slowly about the angular momentum axis as well. But they're moving differently than, they're moving in a different way than the crust. They're moving with respect to the crust. So the actual mode, I suppose I should make a movie. It's something a little more complicated. But there's it's probably easier to visualize to go into the co-rotating frame, where if, now this is the symmetry axis, then we excite the mode, and we have the angular momentum is like this, and then the vorticity, the total vorticity, I suspect, is something like this, and both of these vectors are moving at slow frequency about the symmetry axis. I think that's what the mode looks like. Questions? Everyone's tired.
So I think you're right. These are different limits. I think the limit you're looking at is the ratio you're looking at is the eta in the standard prescription. And so in Constance's model, eta is large. And in your case, it's kind of small. But what bothers me is that I can't see how the standard form for the mutual friction with the beta and the beta prime show up from an unspecified pinning force. You say there's an F naught in the first formula for the vortex motion, and then suddenly there is a usual hydrodynamics mutual friction. I think we need to strengthen that step.
Yeah,
I
agree with you.
Because if we agree that you can do the creep regime this way, then it would be very easy to go back and redo, say, the stability thing that we did with this prescription. The machinery is all there because we've got the B and the B primes, these beta and beta primes, right?
I completely agree with you.
So if we should talk about that and see if we can take that step.
Yeah, I agree with you. At this point, I stop because I don't know how to do this above the vortex level.
No, but maybe phenomenologically we can get some idea for what that would have to be.
Right, I know how to take the perfect pinning limit in this case. I throw this away, I set VL to 0, and that tells me what F naught has to be.
Exactly.
Right, and then that can be put in. You just volume average that. I know how to do that.
So I mean,
So what the approach that I took was say, well, all right, if we take a frictional form like this, conserve vorticity, then we arrive at a perfectly valid and useful parameterization of the vortex line velocity. So then these coefficients take some different meaning, but can be
And
calculated.
that's fine. I just think, you know, the missing step is quite important.
Yeah, there is a missing
So,
step.
but what you're showing is that there is a reason for trying to work it out. Or, you know, work it out, but understand.
I agree.
Thanks.
So there's actually in this limit there is one more mode that's not discussed by Satraki and Wasserman and Cordes.
There are 3 modes?
No, there is a second mode in the weak drag limit. There is also a second mode that could describe precession. The thing is that when you see how the frequency scales with this beta and beta prime, in order to match this to 1 year long precession, then you need something. You need a beta which is really really small, not compatible with, for example, the values we know from Alpha and Langer results.
No, I find only 2 modes.
Yeah, there are 2 modes.
But the other mode is basically the Shaham mode, is what I find.
No, this is in the. I'm talking about the weak drag limit. So
So I think
it's
it's
the limit
okay.
you take as well.
Yeah.
So there is this mode you described, which is the standard, let's say, long period precession.
Yeah.
But there's also another long period mode, but that depends on in a different way on beta and beta
No,
prime.
but then you're saying there are 3 modes.
No, 2 modes.
No, but there's also a Shaham
The
mode.
Sakam mode is in the strong drag limit.
No, but
No,
you're,
the
you're
Shaham mode
talking
is here
across,
too.
across purposes again. You're talking about the same combination of beta and beta
Yeah.
prime as we use.
The Shaham
So
mode
that's
is
not
here.
covered.
Okay, so
The Shaham mode is here, I just haven't written it down. And all of these reduce to quadratic equations, so you only get 2 modes.
yeah, okay.
Yeah,
In
and
my
the other
case,
one, there is no other slow mode.
yeah,
for
it's
this
the other-
limit,
okay,
okay.
it's the when both beta and beta prime are small.
Mhm.
Right. Okay. Yeah.
Right, should we take a 2-minute break or something for a 5-minute break? Whilst Igor says something.